Okay, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1108. Hopefully, you guys are all doing well. Let's make sure I can see the chat. Let's jump in because we were in the middle of examples last time. Let's see, where are we? Where are we? Where are you? Is this it? Okay. Yeah. All right. There we go. Okay, so this is what we were working on last time, and we did it in groups, I believe. So let's actually just run through what the answers are here, and then we can continue. So let's see here. All right, so I asked you about several systems of equations, so inequalities. So we had A, we had B, we had C, we had D, we had E, and they're pretty much all very similar in terms of the lines that were drawn, but the inequalities were changed for each of them. And so put you guys into groups, ask you to figure these guys out. And so let's actually get into that. In terms of the intersection here, what was that?
I got 3, 2.
3, 2. Okay, that seems to make sense. You can quickly check in these equations that you have here whether or not that makes sense. So if your x was 3 and your y was 2, you would get 6 plus 6, which is 12, and that works in the blue line. If you plug in 3 and 2 in the red line, you get 3 plus 2 equals 5. So yeah, that seems to work. So yeah, that was 3, 2. Okay, so I'm not sure who had the first one, but maybe someone from that group can tell me. What regions were we supposed to shade? So these are numbered with Roman numerals because I'm labeling with regular numbers. So this is, region 1, region 2, region 3, region 4, region 5, region 6, region 7, region 8, region 9, region 10. So there are 10 possible regions.
Wasn't it region 10?
And was only region 10?
Yeah.
So, let's see. So we claim that this is region. So we're doing feasible region. Just the part that's shaded like that. And does that actually make sense? Well, we want less than or equal to both of them. So yeah, we actually want this direction under the red line and at the same time under the blue line. And you can test the origin in both and it would work. So you know that they're both towards the origin. So yeah, that looks good. Region 10 was the what we wanted to do here. This one, greater than both. What would that look like? This is again.
Region 1.
Region 1. Okay, so yeah, we want to be above both lines. So it's literally all of that. Oh, and I believe I also asked you, identify whether the feasible region is bounded or unbounded. Bounded or unbounded for the first one?
Bounded.
It's bounded. So remember, bounded means it's possible to have a circle of finite radius centered at the origin that will cover the entire space, so it's very contained. This one, I mean, no surprise, it's unbounded, right? So this is going to be important later because we're going to have certain theorems that's going to deal with whether or not it's bounded or unbounded. This one, what region is here? And again, this is 3, 2. I don't know what group that was.
I think we got 9 as the region.
9 is in like down here.
Yeah, I think I'm wrong though. Sounds like it.
So we want it below the blue line. Someone's trying to get in here. We definitely want it below the blue line, but we want it above the red line. So below the blue and above the red. That looks fine. Clearly this is also bounded. This one?
Region 2.
Region 2. Right. That one says we want to be above the blue line, but below the red line. So yeah, that's the only region that's going to fit. And of course, it's going without saying in all of these examples that we want to be in the first quadrant, right? Because of the x greater than or equal to 0 and the y greater than or equal to 0. So we're always looking in the top right quadrant. Here. So now I want you to notice that the quadrants were not included. So we don't care about x is greater than 0 or y is greater than or equal to 0. So the axes themselves are not boundaries. What would be covered here?
Wouldn't it be 2 and 3 then?
Be 2 and 3. And that just keeps going, right? So that is, of course, unbounded because it'll keep going up in that direction. So this one was similar to this one. The difference is this one, it was bounded by x is greater than or equal to 0 and y is greater than or equal to 0. But here, we do not have that boundary. So the y-axis did not stop us from continuing in this case. Right? This one was bounded. Okay, so overall, it seems like we get the idea, which is good, awesome, because now we're actually going to put these ideas to good use to actually solve some problems in the real world. We're going to move on to right now. I think at the moment, I don't think I have anything else to say about this, but we'll move on to linear programming. So let's see, there we go. So excited. Okay, let's get back here. Maybe a little bit smaller. This is going to be an example. Oh, do I want to move that? No. Yes, I think I want to actually say some things first before we jump into the example. Okay, so the new topic. So we're officially in 5.3 now. This is the main idea. So 5.1 and 5.2 was just us learning about some prerequisite stuff that we will have to be able to do in order to solve the problems in 5.3. But 5.3 is the main attraction in chapter 5. Very useful kind of application called linear programming. So I forgot what kind of journal this was in, but a few years ago, pretty much you had people in industry kind of vote on, you know what's the most useful math out there? Like the math that we need to know in everyday life to actually get stuff done, not stuff that they just teach you and you forget about it. And one of the things was something called the Simplex Method. Now, the Simplex Method is actually a technique for solving linear programming problems. Turns out that it's actually very important to solve these kinds of problems in actual real life. So it's a very important thing. And so, when it comes to applied mathematics, of course, probability is important, statistics is important. Almost everyone uses that. Of course, in other applied mathematics, things like partial differential equations is going to be important. But then I'll get very close in a lot of business applications and otherwise, linear programming is super important. We won't be doing the simplex method. We're actually going to be doing something a little bit smaller. We'll be doing what's called the graphical method. And the simplex method is just something that you would need to know a lot more linear algebra to be able to pull off. So we're going to do examples in 2 dimensions by hand. That's what I'm going to expect you to be able to do by hand. And at some point, I'm going to teach you how to do this in a computer program where your computer program will be using the simplex method. So you don't have to know what that is or how it works, but you will have to know how to actually put it in the program, right? So that's what we're going to do. But by hand, I want to illustrate what is actually happening when we actually solve these problems and what we're finding and why doing what we're doing is going to find that thing. So we're going to do examples in 2 dimensions. In higher dimensions, which means more than 2 variables, we will actually learn to do that in Excel and Python. So that being said, let's continue. Some definitions are in order. So why would you need linear programming? Well, there's a very wide field in applied mathematics called optimization. Okay, so this is the process, study, practice of making a situation. The definition is going to sound very vague when I say it, but I'll explain a little bit more. Making a situation as good as it can be. Right? That's what it means to optimize something. You want to make it optimal. You want to make it as good as it can possibly be. Within the presence of certain constraints. Okay, so what does that mean? So it's like, let's say you're a business and you at this point, you really want to grow the business, you want to expand, you want to make money. So obviously something like maximizing your profits would be very important to you. So then you're going to say, well, my optimization problem as a business owner right now is to optimize profits. I want to make my profits as good as they can be. And then you start to think, well, what does that actually mean? How much profit do you want? Infinity. I want to make an infinity amount of money. Of course, that's not realistic because there are restrictions. These restrictions, we call them constraints, right? So these are restrictions that you have to obey, right? So let's say I'm building a product and I want to make an infinite amount of money. It can't happen. Why? Because to do that, I would have to make an infinite amount of products, sell an infinite amount of products, hire an infinite amount of workers, have infinite amount of storage, and have infinite amount of people to sell that product to. Not going to happen. You're not going to make an infinite amount of money because there's restrictions. There are time restrictions. You're not going to live forever. The business is not going to live forever. There are people restrictions. You can only hire so many people. You can only have so much storage. You can only make so much product. You can only do so much whatever, right? So when you say, I want this situation to be as good as it can be, it's like, well, it can't be as good as it can be, really. You're having certain constraints, but you want to make it, okay, let's make it as good as it can be within these constraints. So let's say I know, you know what, I only have 2 warehouses, I can only hire 250 employees, I can only make so many products per day. How can I make sure I get the maximum profit in that scenario, right? Whenever you have a problem like that, this is called an optimization problem, right? So you have some situation that you want to make as good as it can be, but there are restrictions to being able to do this. And you figuring out a way to solve that problem is called optimization, okay? So now it turns out mathematically, optimizing something often means maximizing or minimizing it. Right? So for example, we're talking about profit. I want to maximize profit. If we're talking about cost, I want to minimize costs. We're talking about taxes. I want to minimize the amount of legal taxes I want to make. Right? We're talking about market share. I want to maximize the amount of market share. A lot of times the best scenario can be described by you making something as big as possible or as small as possible. I want to maximize something or I want to minimize something, right? So a lot of times that's how it's going to happen, right? So maximizing or minimizing, let me be a little bit more specific here, some function, right? So you might be able to write down a profit function or a cost function, or there's some calculation that allows you to compute what is the thing that you're after, what do you want to make as big or as small as possible, right? And so now this is where linear programming comes in. Okay, so this is finding the optimal value of an objective function that is the function we want to optimize So we want to find the optimal value of an objective function where the function is linear. So that's very important. So your function should look like some sort of straight line. It should be able to be written in the form of, oh, a constant times x plus a constant times y equals some function. Or, you know, a constant times x plus constant y plus a constant times z plus a constant times this equals some variable, right? So the function is linear and it is in, and the constraints are linear also. Linear equalities and or inequalities. Right. So if you have something that you want to optimize and that thing is a linear function, and at the same time, all your restrictions can also be described by linear functions, then it turns out you can optimize that situation by doing something that we call linear programming, basically. And this actually happens pretty a lot, right? So for example, if we're talking about profit, and we know that profit is revenue minus cost. What is revenue? Well, for every product we sell, we make $5. What would that mean? Well, it means revenue R is equal to 5 times X, where X is the number of things we sell. 5X is a linear function. What does it cost us to make all these products? Well, for each product, it cost me $2 to make, right? So the cost function C is going to be 2 times X. That's also linear. And so now when I'm like, oh, my profit function is going to be, well, 5X minus 2X, right? Which is 3X, right? So now my profit function is just the function 3X, right? So that gives you a linear function. So you know what you want to maximize or minimize. And sometimes your constraints are also described in linear, right? This is the number of workers I can have, you know, the number of hours I can hire them for is less than or equal to 320 hours among all employees per week or whatever, right? So you're going to have these restrictions and constraints. A lot of times they are linear, both in the objective function and in your constraints. Whenever you're in that situation, solving that becomes what's called a linear programming problem. So that's why it's called linear programming problem, because it's dealing with linear functions. And while these functions are simple, like I said, this is one of the most useful things in applied mathematics. It shows up a lot in real life that you have to actually deal with linear functions, believe it or not. Okay, so now, there are two main methods. To solve linear programming problems. One, there's something called graphically. If in 2 dimensions. And then there's something called the simplex method. In any dimension. Right. Problem is, once you go past 4 variables, 4 dimensions, you can't draw it anymore. You can't visualize something in 4 dimensions. So the graphical way isn't going to work. Like I said, we'll do the graphical. We'll do simplex in Excel, Python. Okay, so for now, we're going to do things by hand. Okay, let's do that example. And I'm going to kind of work through an example here to show you how a linear programming problem would be solved. So this is boom, 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 boom. Paste. Okay. So here's the problem. There's no context given. Just pretend that somehow you care about some problem being solved, and this ends up what it means, right? You have a linear function, right? We'll call it z, right? Is equal to x plus 2y. So this is the linear function that you want to maximize this guy. So that represents something that you want to make as big as possible. Now you are told that you have the following constraints, right? 2x plus y is less than or equal to 22, x plus y is less than or equal to 13, 2x plus 5y is less than or equal to 50, x greater than or equal to 0, y greater than or equal to 0. Okay, so let's pretend these are constraints. There's going to come a point where we're going to have word problems, and we are going to actually figure that out from the word problems and then make up our own problem. But for now, let's suppose we're at this stage, right, where we actually know the problem that we want to solve, right? So let's say it has that. How do you actually go about doing this graphically? So let's do that. How do we do this graphically? Okay, so here we go. Step 1. Okay, so step 1 is to basically find the feasible region. If it exists. If it doesn't exist, it means that you have an impossible problem, can't be solved, which actually happens sometimes. Sometimes, especially when you go to like consultants, like business consultants or something, you'll go and you'll tell them, well, I want to make this much profit and here's my situation and blah, blah, blah. And they'll have to tell you, dude, that's impossible. Like the numbers, you can't do that, right? So sometimes it's like you throw in this problem and it doesn't have a feasible region. It's impossible to get what you want to happen. Happens every now and then, not all the time, but yeah, but you want to find the feasible region first, which, hey, that's what we were working on earlier. So this means you're going to sketch the constraints. You're going to figure out what will satisfy all these constraints. So yeah, let's do that. see. First one, x plus 2x plus y less than or equal to 22. Okay. So not drawn to scale, obviously. This is 2x plus y equals 22, which means the x is going to hit at 11 and the y is going to hit at 22. Okay, so that's that one. Next line, x plus y equals 13. X plus y equals 13. Okay, so x plus y equals 13, which means this is going to hit at 13. That's going to hit at 13. Okay, what else? 2x plus 5y equals 50. So plugging in y equals 0, that means my x would be 25. And if I plug in x equals 0, my y would be 10. So and this is, which one did I just draw? 2x plus 5y equals 50. All right, here we go. Now let's figure out the feasible regions. So what do we want? It's actually less than or equal to for all of them. And it's easy to see that if you solve for y, you would have y's less than or equal to, so you want to be below all the lines here. So I need to be below this, below this, below this. I need to be below everyone, but I need to be to the right of this. I need to be above this. So what region is that? Below everything, but above that, that's this region right here. Right. So far, so good, hopefully. Okay, so that's the first thing. You would find the feasible region. So now, step 2. Find the what we call corner points of the feasible region. AKA vertices. Okay, and this is pretty much where two or more constraints intersect that are on the boundary of your feasible region, right? So this is where 2 or more constraints intersect on the boundary of your feasible region. Okay, so up here, you'll notice what that means. I need to find this point, this point, this point, this point, and this point. Right? These are all the corner points. So I look at the boundary of my feasible region, and wherever 2 or more constraints intersect, that's a corner point for me. We need to find all of those guys, right? Now, finding these involve solving systems of equations, which is why I needed you to review systems of equations. Okay, So let's say I want to label these so we know what we're looking for. Call this V1, V2, V3, V4, V5. Okay. And I might want to actually copy this. Now you won't have to draw two diagrams, but I'm going to draw two, one where I fill in the coordinates after. But you won't have to draw two. Let's see. Okay, so let's go one by one. V1. Okay, what is V1? Well, that's actually 11, 0. That's pretty obvious, right? 11, 0. That was the x-intercept. V2. Oh, that one. Notice that V2 is the intersection of 2x plus y equals 22 and x plus y equals 13. So we need x plus y equals 13, 2x plus y equals 22. Right? So what we can do here is, let's say, call this equation 1, call that equation 2. I can take equation 2, subtract equation 1. This would leave me with x equals 22 minus 13. What is that? 9? Which means that y equals 4. So this means that V2 is 9, 4. So I can go and I can plug that in here. Nine, 4. Okay. Moving on. V3. Now I'll notice, and this is why, as I said, it was very important to actually label your lines, because you're going to want to know who you need to put in a system of equations to find the needed corner points. So V3, you'll notice that it intersects these two lines over here. Right? So again, I have x plus y equals 13. And I have 2x plus 5y equals 50. Okay, so call this equation 1, call that equation 2. What we can do is say multiply equation 1 by 2. Or I guess if you want minus 2. This is equation 1 times minus 2. And then now I can add them. Call this equation 3. What I'm going to do now is add equation 2 and equation 3. So I would end up with, the y's will go away, the x's will die, I'll have 3y left over, and 50 minus 26 is 24. This means that my y is 8. And that would mean that my x is, because I know x plus y is 13, if my y is 8, my x needs to be 5. So that means that my V3 is 5, 8. Okay, now what else? V4, 5, 8. Let me write that in. V3, 5, 8. V4, well, that one's also easy. That's y-intercept, so that's just going to be 0, 10. It's a y-intercept. V5, that's 0, 0. That's the origin. Right? So in this particular problem, we had to Okay, I'm back. I know. Laptop spazzed out for a while there. So can you guys still hear me? Okay.
Yeah, we can now.
Okay, and I can hear you now as well. Okay, so that's good. I got that whole blue screen thing. All right, so we're back. It looks like everything is okay. You can see my screen, I assume. Yeah, we just found all the corner points. So that was actually step 2. So you have something, you know, you want to maximize it or minimize it. What you do is at first, you ignore everything but the constraints. Just focus on the constraints. You sketch them. You find the feasible region, right? That comes down to what we were doing last class. Step 2 is you need to find all the corner points of the feasible region. So once you know what the shaded region is, you look around the boundary and you're going to find all the coordinates along the boundary where 2 or more of those constraints intersect. Okay, and so that's what we're going to do. Some of them will be nice, you'll get for free because they'll just be intercepts, will be very easy for you to tell what they are. But sometimes you'll actually have to go through some calculations, you know, and figure it out. And so essentially now we had 5 corner points here and we now found all of them. Now here is the interesting thing. Here's an interesting fact. In fact, it is a theorem. Okay. The optimal solution of a linear programming problem which I'll abbreviate LP from now on, that's very common, with a bounded feasible region. That's why it's very important for you to be able to identify bounded from not. Will occur either at a corner point or along an edge on the boundary of the feasible region. The latter occurring if the corner points on the end points of the edge are both optimal corner points. And that's very interesting. Why did we need to find the corner points? It turns out that's where the answer is going to be. The answer is either going to be at one of these vertices, or it's going to be on an edge along the vertices. So for example, my answer could actually be, well, you know, V3 is going to be the optimal solution. So really, whatever X is representing, you should have 5 of those X's and 8 of those Y's, right? So that's a possibility. However, if both V3 and V4 are solutions, then it means everything along the edge in between them, everything on that line is also a solution, every point on that line, right? So that's basically what this theorem is saying. If you have a bounded feasible region, the optimal solution the best possible scenario you can end up with is going to happen at a corner point. If it doesn't happen at a corner point, then it's going to happen along an edge. And that's going to happen when two corner points work, then the line connecting those two corner points will also work, every point along that line, right? Which is interesting, which, and I'll probably get to talk about that today, but about why that is, but that's what that is, right? So that's actually a thing. So that leads us to the final step in actually solving a linear programming problem. This leads to step 3. So maybe I should label these guys. So V4, V5, V1. So V1 was 11, 0. This was 0, 0. This was 0, 10. Okay, yeah. So label diagram below. Showing corner points. You only need to draw one diagram in your solutions. So don't think you need to draw it twice. That's not what I'm saying. I just wanted to separate the ideas. Should look like below. Okay. So ultimately, when you're writing this on paper, this is what your diagram is going to be like. You're going to have the picture, the feasible region, and you're going to have labels of the vertices all around that feasible region, or the corner points. Now, it turns out we have a theorem that's going to tell us in this situation, the corner points themselves will be where you look for the solution. And so that's step 3, test each corner point in your objective. Right? What does it mean to test? To actually plug in and find the value. So here we have 5 corner points, right? So okay. So this is X values, Y values, and my Z values. And there is 1, 2, 3, 4, 5, right? So this is for V1, V2, V3, V4, V5. You don't need to draw this column. Again, I'm just doing it to be extra explanatory. But when showing your work, I expect to see all the other columns. Okay, so we're just going to now fill them in. So what are all my columns? My V1 is 11, 0. V2 is 9, 4. This was, is it 5, 8? V3, 5, 8. All right, V4, 0, 10, and 0, 0. And remember, the original function now is where you come back with the objective. So our objective function in the very beginning was x plus 2y. So now, look at the objective function again. It was ignored until this point. everything we've been doing up until this point was with the constraints, right? We sketch the constraints, we find the feasible region based on the constraints, we find the corner points based on the constraints, everything. Now it's at the end that we care about the objective. Oh yeah, remember what we wanted to do? We wanted to maximize that thing. So now what you're going to do is you're going to plug in all the corner points into that thing, right? So if you have x plus 2y, your x is 11 and your y is 0, you would get 11, right? Yeah. X plus 2y, so that would be 9 plus 8 in this case, so that's 17. X plus 2y, that would be 5 plus 2 times 8. So 2 8 16, and you add 5, so that's 21. X plus 2y is 20, and x plus 2y if x is 0 and y is 0 is 0, right? Now, we remember what we want to do. We want to maximize, so we're going to take the maximum value. This line. Max z value. It turns out this is the optimal. So now, step 4, which is the easy part, but part that people often forget, state your solution. The optimal value is z equals 21. This occurs at x comma y equals 5 comma 8. And that's your answer. So if someone were to ask you the question, I have these constraints and I want to make this function as big as it possibly can be, what's the biggest it possibly can be? It turns out 21. It's like, okay, this is my profit function. I want to make $50 profit. Impossible. Most you can make is 21. Here's why, right? Because of these constraints, the biggest that can be is 21, right? So, and you'll be able to know that, and you can know that, and then you can make plans based on that, right? So that's the answer. That's how you do it. That's how you solve a linear programming problem. Next time, and I guess I'll leave the other examples underneath this in case you want to check them out in the notes and try it for tomorrow. But next time we're actually going to start even higher than this. We are going to start by reading a word problem, translating it into a problem like this, and then solving, right? So these problems are very involved, which is why I told you, make sure you're really good with systems of equations, go back, review, because you're going to have a lot of stuff to take care of. And the faster you are at the algebraic computational stuff, the better, right? But that's it. This is the biggest this function can be, and I can tell you what you need to make x and y be in order for that to happen, right? So you can say, oh, x is the number of employees, y is the number of products they make per day. This is my profit function. What's the most profit I can make? $21 a day, and you need to make that by hiring 5 employees and make sure they make at least 8 products. Right? So that was just an example, just a random example, just made up. But we will see some more examples next time. Hopefully that was clear. I'm going to let you guys go. Yeah, I think thumbs up. So with that being said, thank you for your attention. Sorry for the technical difficulties. I will see you guys in the next one. Ciao.
Thank you.
Professor, can you hear me?